Hey guys, welcome back. We calculated a bunch of statistics in video one, but to get a better understanding of what we did, I think it's best to probably visualize the results. To do this, we're going to start by creating a mean versus standard deviation plot of the 47 industries, the market portfolio, and the equally weighted portfolio. And after that, we'll begin building and plotting the efficient frontier given our sample data. The way we're going to do that is in two parts. First, we're going to calculate the global minimum variance portfolio, or the nose of the bullet of the frontier. And then second, we're going to calculate all portfolios with a minimum variance given an expected return. And then lastly, we'll add that efficient frontier to the plot we've calculated in part one. Okay, we're back in R and are going to begin by plotting the statistics calculated in video one. And when creating a plot in R, I think it's best to think about forming the plot in layers. That is, each line of code is executed, something else is being added to the plot. And then also within the help section, just typing in the plot function can give you some helpful tidbits about the arguments. So let's get started with the plot function. The first two arguments of the plot function are the x and y coordinates of the points in the plot. And for now, we're going to use 0, 0 as a placeholder because we're later going to fill that in with the efficient frontier. The third argument we're going to use is ylim, which defines the length of the y-axis, and we're going to combine that with our range function and our combined functions to say that the y-axis is between 0 and the highest of the 47 industry returns. And the fourth argument is the same thing, but with the x-axis, and we're going to say that's a range that's defined between 0 and the highest standard deviation of the 47 industries. And then the fifth argument is going to be the label on the x-axis, which is denoted with xlab. And we're going to say that's an expression equal to sigma. And then finally, we're going to add the y-axis label, which is ylab equals expression. And we're going to paste in mu quotation minus the risk-free rate. Now let's execute this line of code and see if we have a plot populated. Great. So we can see the x and y labels as well as the definition of the x and y axis as we would like them. The next layer to the plot will be adding the means and the standard deviation to the 47 industries. This is simply done with the points function, and it just adds points to a plot. So points, and it does it on an XY basis as well. So we want standard deviation on the X axis. So we'll start with that, and then mean return on the Y axis. And let's execute that line of code. And you can see the 47 industries mean and standard deviations have been plotted. The third layer of the plot will be to add the equally weighted portfolio and the total market portfolio. This is again done with the points function, but we're going to want to plot them together. You'll see in a second why. And on the x coordinate basis, we're going to use the standard deviation of the equally weighted portfolio and the standard deviation of the total market portfolio. And we're going to combine that on the y coordinate basis with the mu return of the equally weighted portfolio and the mu return of the total market portfolio. And we want those two portfolios to look differently. So with the PCH argument, we're going to set that equal to a star, so they'll look like stars rather than dots. And then with the color argument, we're going to make them blue, equals quotation blue, and execute that line of code. And you can see that both portfolios have been added as blue stars. It's great we were able to make the two portfolios look different than the 47 industries, but I don't know which portfolio is which. To solve this, we're going to use the text function, and like the points function, the first two arguments refer to the x and y coordinates where the text will be written. And for the third argument, we're going to use labels, combine, and use that with the C function or combine. And we're going to call the equally weighted portfolio E and the market portfolio M. And let's change the color on that, and we'll set that equal to, let's say, red. And we'll use, lastly, the position argument, which tells you where the text is written in relation to the coordinates. And let's say we'll use, again, the combine function and 3, 1. And let's execute that line of code. And great, you can see the market portfolio is right here and the equally weighted portfolio is labeled correctly. For now, the last layer to the plot we're going to add is the title. and this is simply done with the title function. And then the first argument is the actual title text. So we'll say figure 1, industries, market, and EW for equally weighted. And then the second argument we're going to use is the line, which determines how far off the title is from the actual plot. And let's execute that. And you can see that the title has been populated. That completes our data visualization for now. We're going to put this on the back burner until we compute the minimum variance portfolio in the efficient frontier, and then we'll return to plot that. This tutorial isn't focused on the mathematics behind the efficient frontier, but I think it's important to return to this PowerPoint and understand the intuition behind calculating the MVP and the efficient frontier. So the optimization program for the minimum variance portfolio is right here, and it's pretty much saying that we want to minimize the variance of the portfolio subject to the 47 industry weights equaling 1. So if you set up a Lagrangian function to solve the optimization program and then take the derivative with respect to W and set it to 0, you end up getting that the optimal MVP portfolio weights is equal to or is proportional to the inverse of the covariance matrix. So once we calculate the optimal weights, it's easy to calculate the mean and the standard deviation of the MVP. We will now assign these variables, AA, BB, CC, and delta in R, and then use them to calculate the optimal weights along with the mean and the standard deviation. We start with calculating a covariance matrix for the 47 industries, and we're going to assign a variable to that. We're going to call it covmat for short, and we're going to use the covariance function in our returns data set, again subsetting from the second column to the number of industries plus 1, and we just need to remember to multiply this by the number of trading days per year to annualize the figure. And we'll execute that line of code, and then we'll calculate the inverted covariance matrix, again assigning a variable to that, and use the solve function to calculate the inverted covariance matrix. And we'll execute that. And the last thing we need to do is assign a vector of 1s equal to the number of industries. So 47 1s we need, or a vector of 47. We're going to use the repeat function, and we're going to say repeat 1, the number of industries, which is 47. We'll now assign values to the variables we saw in the PowerPoint. We'll start with AA, and that was the sum of the inverted covariance matrix. And then for BB, the computation was a little more complex. There was the transposed vector of the 47 industry mean returns multiplied. The notation here, percentage sign star percentage sign, is just the notation to multiply matrices. And that was multiplied by the inverted covariance matrix and then multiplied by a vector of 1s. And then for CC, similar calculation, transposed vector of the 47 industry returns multiplied times the inverted covariance matrix multiplied by the vector of the 47 industry returns, MUM. And then finally, delta, which the computation here is AA times CC minus BB squared. We'll go straight into calculating the global minimum variance portfolio given the equations we saw in the PowerPoint. And we'll start with the optimal vector of weights, and we'll denote that variable WG, and that was the inverted covariance matrix multiplied by a vector of 1s divided by the variable AA, and then we'll see what value that returns. So you can see down here in the console that these are the optimal percentage weights of each industry, and there are no short sale constraints. Next calculation, we'll calculate the mean of the minimum variance portfolio, and we'll assign that a variable MUG, and that is simply BB divided by AA, and we'll return that value. And the average return of the minimum variance portfolio during our sample period is 11.4%. And finally, let's calculate the standard deviation, which is just simply the square root of 1 divided by AA. And again, let's return that value. Let's call this sig G. And the minimum variance portfolio or standard deviation of that portfolio is roughly 10%. The final computation before plotting is that of the efficient frontier. We'll start by calculating the average return of the frontier, and we'll assign a value mu front, and we're going to use the sequence function, which is essentially saying that the efficient frontier's return is going to span from the minimum global portfolio return to the maximum of the 47 industries. And the length of the sequence we're going to define as 200. Next, we're going to calculate the standard deviation of the frontier as a quadratic function in the mean return of the portfolio. And we're going to assign a variable to that, and we're going to call it sig front is equal to the square root of the variable cc minus 2 times bb times the efficient frontier mean front, which is denoted as mu front. And to that is going to be added AA times mu front squared. And then all of this is going to be divided by the square root of delta. I went ahead and updated the plot, replacing the 0, 0 placeholders with the efficient frontier calculations we had made. I also added the global minimum portfolio into the syntax within the equally weighted and the total market portfolios. And if you take a look at the plot, you can see that the global minimum variance portfolio has been added along with the efficient frontier. This is the end of this video in data visualization and analytic solutions to portfolio optimization. I hope to see you in the next video.